So thank you very much for giving this opportunity. So this has been a very long exercise for me. In fact, the roots go back to my postgraduate student times in the late 60s in Helsinki. But the real breakthrough occurred first in the mid-90s. So that now we now actively worked on this theory and the basics on that for more than 25 years already. So that basically there's nothing completely new, but it's a kind of new way of putting together the pieces we have found during the years. And the key in the exercise is in finding the simplicity behind the complexity we have used to see. I often start with a kind of historical connection, and now I like to take the share screen mode and screen 2. Just a moment. Here we go. And I share this screen here. Okay, here we go. So I like to start with antics. Antic observations of planet didn't fit.
I can't see the shared screen, Paavo.
Yeah, me neither. We did try it, so.
Okay.
It was working just now because I saw the
share screen
when I joined.
Share. How about now?
Okay. Yeah. Okay.
Now
that's fine.
Yeah, it was my fault. I had to push the button. Okay, let's go back to the antics first. So antic observations of planet didn't fit with circular orbits. So the orbits were modified with epicycles. Eudoxus, who was the father of the epicycle model, considered epicycles just as a geometric tool for the illustration of planetary motions. However, in his metaphysics, Aristotle describes Eudoxus' model as the real mechanism of planetary motion. So he in some way expressed that like being a feature of nature itself. So then late 19th century's observations of light and fast-moving objects didn't fit with linear time and space. So time and distance were modified with time dilation and length contraction. Einstein stated that distorted time and distances are the explanations which are needed for the relative explanation of relativity of observations are considered as real properties of nature. And this is a citation I found from Einstein's lectures in Berlin in 1911. Length contraction really exists insofar as it doesn't exist for a co-moving observer, though it really exists in such a way that it could be demonstrated in principle by physical means by a non-co-moving observer. So it takes quite some time to really understand what he meant with this. But let's go further. By setting Earth at the center, Ptolemy astronomers lost the structure of the planetary system and the observer's motion in the system. So the solution here was Copernicus, who introduced a system-oriented perspective of the sun and the planets, which disclosed the effect of observers' location and motion in the system, and allowed a dynamic solution of the planetary system. Now we take the next step, which is here, by describing space as a three-dimensional surface of a four-dimensional ball or sphere. The dynamic universe model allows a dynamic solution of whole space, which relates observers' gravitational state and motion to the space as whole. And let's see how it works. Oh. The barycenter of spherically closed space is at the 4 center. So I describe it here. Any mass m in space is subject to gravitational force towards the barycenter. Towards the barycenter and the corresponding gravitational energy. So we are now looking at the situation of mass m at the surface of the ball here. To prevent a collapse, the gravitational force can be balanced by the cosmological constant, which was suggested by Einstein in his 1917 for a static solution. But there's an alternative to that, and it's by interpreting the rest energy of mass m as the energy of motion, as we can put it in the form is C times P, the same formula as we have for electromagnetic radiation, which is the mc to the second. Motion balancing the gravitational energy in the dynamic solution. Equating the energies of gravitation and motion allows solving the dynamics of the structure and the expansion velocity c. We simply make an equation of these two energies here. And what it was, when we use 14 billion light years as a radius here, and the mass density, which is roughly the Friedmann critical mass density, we end up with c, which is equal to the velocity of light. Quite a surprise. When I found this, it was quite a surprise for me that it works that simply. So it means that space acts, as we can see, its solution gives plus minus signs, so that we can consider the whole structure as a pendulum in the 4th dimension, a spherical pendulum. Now I jump over this, we go to this. So starting from a large radius, long time ago, in the past, we get motion. Mass in space get motion from its own gravitation. So the whole structure contracts close to a singularity and turns back to expansions, which we are living right now. And first we got the energy, the rest energy of matter, which now is interpreted as the energy of motion in the 4th dimension. We get the energy in the contraction, and now we release it back in the ongoing expansion. So the cycle of physical existence has started from the emptiness in the past, and it ends up to practically to emptiness in the future. And let's consider, it means that we don't need instant quantum jump or Big Bang to get started. But the rest energy of matter is the energy of motion obtained against release of gravitational energy in the contraction phase preceding the expansion. The present interpretation of space, of the expanding space, is that local systems like galaxies and planetary systems conserve their dimensions, so they don't follow the expansion. But when they follow the overall conservation of energy, we can find out that local gravitationally bound systems expand in direct proportion to the expansion of space. And in fact, there are a lot of proof to show that the local system expand, although in present cosmology, there are correction factors, kind of epicycles, which eliminate the obvious indication of such expansion. I don't go into detail right now. So in the present theory structures, the velocity of light and the rest mass of matter are considered as natural constant. But the velocity of light is linked to the 4D velocity of space, and the rest mass to the motion in space. And there will be extremely important finding that mass is a kind of substance for the expression of energy. So it's not a form of energy. Mass is measured in kilograms and energy is measured in joules. And they are not the same thing, but mass, when mass is energized with velocity or through the presence of other mass in space, it has the gravitational energy and the energy of motion when being in motion. And as one of the consequences is that the reduced frequency of atomic clocks by motion and gravitation is explained with dilated flow of time. So that's what we do in our present theory of relativity. But in dynamic universe, we can find out the energy connections. So the reduced frequency of atomic clocks by motion and gravitation is explained by the quantum mechanical solution of characteristic frequencies, which says that the characteristic frequency is proportional to the rest energy of the oscillating electrons in the system. So we don't need dilated time or contracted length. And it makes the philosophy, or let's say the picture of the whole understandable. So let's go what happens now. We were discussing the homogeneous space, so that all mass was uniformly distributed in space, so that there was no motion in tangential directions here, so in space directions. The only motion was as the expansion of the sphere, and we have the basic energy balance here. So how to get local mass centers and motion in space by taking care of the conservation of energy. We have to conserve this balance here. So the solution is quite simple. Local bending of space makes that, so we get the velocity of free fall as an orthogonal component of the local velocity of space in the local fourth dimension. And now we have we conserve the basic energy balance, and our local fourth dimension is in a little bit different direction here. How to get, oh sorry, I just noticed that the text is in Finnish, but
no problems. It's the equations that I'm interested in.
Sorry?
It's the equations that I am interested in. I'm not very good at words. I much rather see symbols.
Okay, so that.
Oh, that's fine. Yeah.
Yeah, the basic is the energy balance, so that we have the energy of motion, energy of gravitation, and sorry. So this slide was made to try to minimize the equations. I'm sorry for that. Let's see if I have the same.
No, don't worry. Don't worry. It's fine.
Okay.
Because it's the equations. I don't know whether you've understood my English, but or my accent or whatever. But I'm much happier with equations, because then I can interpret the equations and listen to what you're saying. Yeah.
So here I simply divide the gravitational energy and energy of motion into two orthogonal components, and we can now express the local rest energy also in terms of the local gravitational energy due to the rest to the global mass, so mass all in the rest of space here. And we can find out that the rest energy can be expressed with a gravitational factor delta here, which is gm divided by r to the times c to the second here. I'm very sorry to.
Could I ask you why you write C dot delta MC? Why do you split the two
C dot, it's because zero here means the velocity of space in homogeneous space. And here C, the local C, now you can see that local C close to a mass center is smaller. So C is smaller than C by the cosinus.
Okay.
And in fact, this what makes the gravitational factor of atomic clocks. So we can find out that the clock frequency is proportional, in fact, to mc, because we can find out that in Planck constant, there is a hidden c inside the Planck constant, so that instead of being proportional to the rest energy, or c to the second, the frequency of a clock is proportional to c, and that what makes the gravitational factor to the clocks. And in the case of gaining motion at constant gravitational potential, we can't do this trick as we did here, but instead we need to bring some external energy to get motion and momentum, and the arrow here describes the total energy, which can be expressed in form E on m plus delta m times c to the second. And we can find out that when we make a full analysis of this balance here, we can find out that the rest energy of a moving object is reduced, and we can describe as as reduction of the rest mass. Mass can be considered as a wave-like quantity, and it can be handled as a complex quantity, so that now we can understand also the effect of motion to atomic clocks, because again we are reducing by the factor of 1 minus beta to the second the rest energy. But also we can observe that any velocity in space is central motion. Any motion in space is central motion relative to the center of the sphere here. So it means that the central force created by the motion reduces part of the gravitational interaction with the rest of space. And it means that the reduction of the rest energy is exactly the inertial work we make when obtaining motion in space. And it's exactly the mass principle. And now we combine these two effects, we can find that the rest energy can now be expressed in form of reduction due to gravitational factor here first, and other factor due to local motion. And it also means that the frequency of atomic clock is subject to same reductions due to gravitation, local gravitation, and local motion. And it corresponds to the Schwarzschild solution used for atomic clocks close to a local mass center. This leads to very similar picture of local space as what we have used to see as the profile of space-time in general relativity. But in fact, we can now, starting from the hypothetical homogeneous space, we can see that any system, gravitational system with local motion, minds a certain part of the original rest energy. so that the deeper we go in space and into local phenomena here, the smaller is the available rest energy for certain mass objects. And we can express, now we don't use time and distance as parameters for describing relativistic things, but we can use the energy state. And it also means that now the behavior of clocks is explained in absolute time and distances, coordinate quantities, which are essential for human comprehension. And we can fully understand the relativistic phenomena. So we don't have any logical problems with relative velocities, but we always have a fixed reference for any experimental setup. And just to summarize the effect of motion and gravitation on atomic clock in the relativity theory of relativity, the flow of time is observed changed in clocks moving at different gravitational state relative to the observer. The rest energy of electrons in the clock is unchanged in this framework, so that our formula looks like this. So comes from Schwarzschild solution. In dynamic universe, as shown by quantum mechanics, the frequency of atomic clocks is a function of the rest energy of oscillation electrons in the clock, and of course the quantum states here. Conserving the overall energy balance in space, local gravitation and motion reduces the frequency of clock according to this equation here. And let's have a look at the Planck equation, which I mentioned already. It's useful to notice that we generally express Planck's equation in form is energy is h times f, but of course f is 1 divided by t, the length of a cycle. So it already gives a hint to the direction that it has. The quantum has some close connection to the length of a cycle, to one single cycle. So this equation is a standard equation from any physics textbooks for a dipole antenna. So it's the power of radiation emitted by a dipole antenna. The only thing I need to do, so this has nothing, no assumption bound to the dynamic universe theory, which I explained, but it could be done simply from existing physics. So we express the dipole moment here, and then we clean the formula by first using instead of omega, we use f, and also use lambda, the wavelength in certain, and instead of epsilon zero, use mu zero here. And when we do this, the power equation looks like this. And as radio engineers do, this is the number of electrons in the dipole, n to the second. This is the length of the dipole related to the emission wavelength. We make relate the dipole length to the wavelength. This is a typical Hertzian dipole geometric factor 2/3, and then we have the factors 2 times p to the third, e the unit charge to the second, mu naught, and then c times c to the second. And next, what we do is that we solve. This was the power, which was watts joules per second, and now we divide that with f. So we get the energy emitted into one cycle. So this is the number of electrons, there's a dipole length, there's the geometrical factor, and we can now see that there's one of the F is reduced, and we can see that there's C inside the Planck equation. And we go further here, and we can also see that if we set the number of electrons 1, there's only one electron oscillating in our dipole, and we set the geometrical factor instead of 2/3 close to unity, we can find that we get exactly the Planck constant here. But when now I have defined H0, which I call intrinsic Planck constant, where we have taken out C out of that. So the Planck equation now takes the form H0 divided by lambda, which has the dimension of mass. So it is mc to the second. And one question here is that we related the dipole length to the wavelength emitted. If you consider a point source as a dipole in the fourth dimension, so in relativity theory's framework, the extension or line element in the fourth dimension during one cycle is exactly the wavelength. So we have one wavelength, any point source can be considered as about one wavelength dipole in the fourth dimension, which now explains the practically isotropic antenna here. And when we continue from here, we can find out that it has exactly the Compton wavelength also now energy expressed with Compton gives a simple form by using the H0, because now we had eliminated one of the C's there. So it's mc to the second, mc to the second. And what is very interesting here is also that the fine structure constant now gets a form of pure numerical or geometrical factor. It's not connected to any physical factors anymore, because once we have to open the Planck constant and the connection between the electrical constants and the Planck constant. And it means that we can now express all basic forms of energy basically in the same form. So everything can be expressed as m times c to the second. And now we can already see that mass can be expressed as h bar 0 times k, which is the wave number, times c to the second, or also applying Coulomb energy and fine structure constant here. A unit cycle of radiation is here. It has the form c times p, and the rest energy or mass as we have used to have it, but it also can be expressed in terms of the wavelength or wave number here, and kinetic energy also can be. And what is interesting here is that, as you can see, mass is the first order factor in each of these expressions. And in fact, that was guided me to consider mass as the substance for the expression of energy. Wherever you have energy, you have mass as the first order factor here. But also you can see that by looking at the dimensions, so that joule is kilogram times m divided by s to the second, so that mass is there as the first order factor. Okay, so this was a kind of some of the very basics. Now I like to see what it is as a general. If I compare now the two approaches to build to build a theory, we can follow the traditional way, which is based on force, kinematics, and metrics. The alternative way is to start from energy and dynamics. So we honor time and distance as coordinate quantities, which are essential for human comprehension. And we can see the dramatic simplification which we have in all the system. Here, traditionally, we start from Newton equations, Newtonian expressions, but instead of energy, they use force as the basic quantity. And from that, we need the theory of relativity. We don't have any need for relativity theory, separate relativity theory, because as soon as we take into account the effect of the rest of the space to any local phenomena, we have relativity there already included. So there's no need for a separate relativity theory at all. But predictions for cosmology becomes simpler and more accurate and without any additional parameters. We don't need any dark energy or other additional parameters, but we can see that following the zero energy concept throughout the system, we can get simple, precise predictions and an understandable picture of reality. We can go further to quantum mechanics directions, following the idea of mass wave. And we can find out that the concept of mass wave very much corresponds or is a kind of replacement to wave function, which we are used to use in quantum mechanics. But we can see that we can eliminate a huge number of additional postulates, so that the number of postulates is radically reduced. So that essentially we have started from the spherically closed space, and then we follow the zero energy concepts and take care that the zero energy balance is conserved in all actions, in all energy conversions that occur in space. So that is very, very shortly now some of the key features of my thinking.
Yeah, very interesting indeed. Because what I have been doing actually is coming in from the other way. In other words, starting at the bottom, taking energy as the basic concept.
Yes.
And starting from the quantum ideas and slowly working my way up into classical mechanics. So it would be interesting to see how those two ideas relate to each other.
Yeah.
You're coming very much from top, what I call top.
I start from the whole and go to the details. Yeah. That's true. But in fact, it works very well with the quantum ideas, because there we have this kind of system approach, and we on the conservation of energy. There are a lot of consequences then in the cosmology area, which become very much simpler and more understandable. But also in quantum mechanics, I think that I can demonstrate. Let's see, the mass wave concept. Let's show here. Oh. No. Sorry. I have to take it here, I have to take it here. Now we go here. How it works in a very simple way. So you can see this equation. It's simply for hydrogen atom, this the kinetic energy and Coulomb energy. And then we put in as the key assumption is the resonance condition. And we express the same equation here. Same equation here. Here. So I have simply written the same equation using...
Now, yes, excuse me interrupting. I would very much like to go into the details of this myself privately, actually, because it's coming in very much, Paavo, with the quantum potential, you know.
Yeah.
I think there's a link there with what I've been doing through the quantum potential. Sorry to interrupt you, but could you go on? Just explaining that new equation you've put in.
Yeah, I simply then look how this equation looks like. And we can see that the energy fulfilling the resonance demand, it's a continuous function, but we can find out that the minima of the continuous energy are the quantum states exactly. We can solve them mathematically as well, and we get so-called relativistic solutions. And this is philosophically, I think this is very, very important because it states that energy itself is not quantized. We can find that the stable states, they typically take the certain quantized side. What is quantized and is the resonance condition, and in general, also we can find that any antenna, it's not energy sensitive, it's frequency. So it's frequency sensitive, not energy sensitive. So that it's a kind of so that energy states look like being quantized. The minima of energy states are quantized, yes. And so it means that also that the probabilities in quantum states are essentially similar than probabilities in thermodynamics, so that the system tends to take the energetically most favorable state, and then it looks like being quantized.
Very interesting.
Also,
there's a lot of food for thought here. Yeah. Okay, let's have a look at the double slit. Good.
This becomes very, very simple because once we have observed the resonator concept, any mass particles can be considered as a Compton wave resonator. And we can when we look it in one direction, we can see it as a system with a standing wave here, mass wave. When we put the mass wave into motion, we know that the wavelength is increased a little bit by the motion. And what happens to the resonator is that now the net momentum of the front wave and back wave becomes little bit different, and we can find out that we obtained the de Broglie wave as the net mass wave of the resonator in motion.
Can I just come in there, Paavo? Paavo?
Yes.
Yeah. Yes.
Have you got to sleep?
I don't know. I just put on off my sound because
But you notice this is very close to my forward and backward derivatives, don't you?
I didn't notice immediately, but now that you say it.
I think not surprising that, but it means that the Broglie wave is following the particle here. And now it doesn't matter which hole the particle itself takes, because the wave anyway passes through the hole, both of them. And what we are at the screen here, we are not detecting the particle, but we are detecting the kinetic energy it brings. And that follows the waveform, the interference pattern here. So that it's very simple.
Well, you see, but this is very interesting, because this is exactly what I've been trying to tell Paavo, but from a different point of view. And I think the interesting thing is going to be to explore the relationships between the two different points of view. Because I don't come in with a standard approach at all. I'm coming in through what I call an algebraic approach, which I could explain. But with that particular approach, there are no waves. There is only energy, and momentum.
This was quite a surprise for me that it became that simply.
Yes, but I think there's a reason for it. I think there's a reason. Well, it's got to be a reason for it. But it could be. I'm not going to say it is, but it could be what I've been struggling with.
Okay. Yeah.
But I think that's something that can be thought about and talked about and researched.
Yeah. So my focus has been in general physics and cosmology.
Yes,
and paid far less attention to the quantum mechanical issues. But I think that the concept of mass wave and the kind of simplicity of thinking here might be helpful also in
absolutely, definitely. Because already I've got some ideas that I want to explore.
Yeah.
I've already got some ideas, but it'll be different. But it'll have the same characteristic features.
Okay. Yeah.
Because I think it's putting it into waves really is a distraction when you're coming in from bottom up.
Yes.
But I mean, what you've done is you've gone from top down, and you said, well, I've got this interesting principle. Now I've got to fit it in with this damned wave stuff that they're talking about. So you forced your principle into the wave theory rather than into what I've been doing is the algebraic theory, which is thinking only about energy.
Yeah. Okay. Yeah.
And of course momentum, because
momentum.
The energy momentum tensor is key.
These are the key factors, and one confusion in standard physics is that they are so much focused, and they have taken force as the
that's totally wrong. That's totally wrong.
Yeah, it's certainly wrong, because force is just the gradient of potential energy or the change of momentum.
Yeah.
Yeah, and that was one key thing which I needed in getting to the right basic postulations in my theory structure. In fact, I have tested the theory on the cosmology side very, very, very carefully, so that there are very, very interesting findings there.
Yeah, good, because that's not where my expertise lies. I'm of course interested in the cosmological, but I've concentrated much more on the bottom. I've been concentrating on the bottom.
Yeah, we need both. We need both approaches.
But you can only go so far, you see. You need to be pulled out at the bottom, just as you've been forced to be pulled out from the top.
Yes.
To get to the bottom.
Yeah. A key point in the top approach is that we can find out that what we call relativity it's a direct consequence of the conservation of energy when we take into account the effect of the rest of the space to local phenomena. And the system of nested energy frames, that's the key in working with that.
Yeah, and this is the whole idea of David Bohm's idea of wholeness. Because the wholeness is the gravitational field, which is not talked about in the quantum approach at all.
Yeah, that's right. Yeah, but now what is interesting here is that we can find out that the local rest energy is always balanced by the gravitational energy of the rest of space. And
that is a puzzle that I have been having for a long time. Rest energy.
Yeah, and so that there's no need for antimatter or anything. The rest energy is balanced by the rest of space.
And that means that we've got to think very carefully about what the meaning of space will be in the type of theory that you're discussing here. Because occasionally I see you putting it in as if it's matter. Do you have anything like a vacuum, the concept of a vacuum state? Does that come in anywhere?
That's a very tough question, because I can also see that the basic form or mass is unstructured wave. So basically, what people are trying to find in space is the dark matter. So I think it's unstructured mass, and what makes it particle is that it must be localized to form a resonator. That's the point.
Yeah, but it may not. I mean, we might not need to force it into a particle, you see, because do we have to have energy carried by an agent? Is the question that I've been examining. Because normally we say, yes, it must. If the energy is carried away as kinetic energy, there must be a particle carrying it away.
No, we don't need. So that we are used to think that, and we describe electromagnetic radiation as a transversal wave. I could consider that mass wave propagating in space is more like a longitudinal wave, possibly. I haven't studied that in detail, but as a, let's say, rough idea.
Well, the biggest problem I see in the physics community is they want to say everything is a particle of some nature or other.
Absolutely, I completely agree with that, and we can now see that any particle, in fact, is a wave package.
Yes, it's a structure. It's something that's non-local. It's because the whole point about energy is that it needn't necessarily be localized.
Yeah, that's the way of localizing. Yeah, and that's why Planck, the Planck unit, that's the point where the gravitational energy and electromagnetic energy meet each other. I think that's the key. That's the key. And if you go to our Physics Foundation Society web pages, my colleague Ari Lehto has made a fantastic finding already for 40 years ago, that there is a kind of period doubling mechanism which which demonstrates the build-up of different particles, starting from elementary particles up to cosmological structures and planetary structures, so that the same doubling period works all over the scale.
Right.
And once again, there's certain simplicity behind all the complexity we see.
Agreed. Paavo, have you got it?
Well, some of it, sure. I mean, yes, it is interesting. I think I guess what I can tell is that somehow, I guess Basil wouldn't emphasize the wave concept as much as Tuomo. Would that be correct, huh?
Well, that's correct, but that's what I'm saying. I mean, I don't. He's forcing it in because he feels he wants to see where the obsession with waves fit in to the principle he's dealing with. And I don't think you need to have the waves. The idea of the resonator is interesting, but it's not necessarily a wave. You see, it's our quantum blobs that we talk about, Morris and I.
So you can do the two-slit without waves.
Oh yes, well we do it. That's what Chris Dewdney does but he's using force, and the point is that when you use force, it doesn't give you a nice clean description. It must be energy.
Yeah, exactly. That's very, very essential indeed. So that there is no conservation law for force. There's a certain law of balance, local balance. Force is a local quantity. Energy tells the history, how velocity has been obtained. It tells how it's obtained, where it comes from. Energy velocity in space has its history.
Yeah. In that sense, the energy is local. It's not localized.
No.
It's a global feature, and this is what we want, Paavo.
Exactly. Yeah. It's very, very interesting that you have made the same conclusion starting from the.
So I came from the bottom. It's just looking at the mess that the physicists have made of the mathematics.
Yeah, exactly. Yeah.
And then you see that it can't be there's no such thing as a particle. A particle is a construct from a deeper idea.
Yes.
And the interesting thing in your work is that you've come to it cosmologically downwards.
Yeah.
And because I come from it from the bottom upwards, it's very difficult to see what this global principle is. But I think you show it very nicely. But I can see why physicists would have difficulties with what you're trying to do. And that's their problem. That's their problem, of course. But
I have very certain. My experience, you may know that my background is in industrial physicist work. Basically, my professional work has been technology. I've been working for semiconductor technologies, that kind of thing. And people with technology background, they have very easy to adopt my thinking.
Yes, I agree.
But because they like to understand the phenomena, they like to figure out how they work in practice. But it's very, very to get physicists interested. The first reaction is reaction, because they say that we already know how everything is.
Well, this is what I call the arrogance of the theoretical physicists.
Yes, it has been very, very tough for me.
And they are very arrogant people.
And some way I feel that it's better approach, because this is a very, very holistic approach.
Yeah.
So it's better to look starting from the philosophy. So this is philosophically sound to start from the whole, and also to make to minimize the postulates. And also for me, it was one of the key issues in the very beginning, was to understand the nature of coordinate quantities, time and distance. So for human being, understanding means that you have to answer the questions where, when, and what, where, when. So that space and
but the physicist and the professional physicist is expecting a different answer to those questions. That's the problem.
They try to interpret the reality behind the mathematics, but when the mathematics is formulated from certain very strange starting postulates, it doesn't work that way.
Well, I think it doesn't work that way because we don't teach the mathematics properly. You see, the mathematics is really a set of tools for describing something. And as you know, if you're describing something and you've got the wrong tools, you get into a terrible mess.
Yes.
As a technician, as a technocrat, you also know that, because unless you get your tools right, you're not going to produce what you want to produce. And so we mathematicians have to look very carefully at our tools. And I think the trouble with the physicists is that they do not look at the tools. They take the tools that are given to them and use them, and they abuse them, actually, in my opinion. And you'll find a very few of them really know what they're talking about.
I see.
And they're the people who become household names.
Yeah.
So, Paavo, where are we going to take this? You're the man who put us together. And we've got some agreements here in the sense that we both see the importance of certain questions, wholeness, top down, bottom up. And they have to be brought together. Perhaps more clearly, expand out the consequences of concentrating on energy momentum and not on coordinate systems.
I was very, very delighted to hear from you that you appreciate the energy as the key quantity.
Well, because I've been trying to say this to my colleagues in academia. And some of them look at me as if I've come from Mars. But there are others who are actually moving in this direction.
It's very strange that physicists try to find a unifying theory by combining forces. It doesn't make any sense, at least for me.
No, it doesn't work.
As you could see here, that expressing the different energies with the same formalism is far more simple and more illustrative.
Yep. No, I mean, I can see why a lot of physicists would say, "Well, as you said,"
exactly.
Because they haven't really thought about the amount of time in the area that I've been interested in, people are worrying about the measurement problem. And there is no measurement problem. They set up an artificial problem and are trying to solve it. And then say, well, I can't solve it. Of course you can't solve it. It's a wrong ruddy question.
Yes, I completely agree with that.
But I don't know what you can do about it. They all do it. They all teach it. I'm at University College London, which is got a very good physics department, and the majority of the physicists there will not listen to what I'm saying.
Some of the authorities in physics in Finland, in Helsinki University, they have simply refused to read my writings. They say that it's unnecessary, that they got this kind of proposals, new theories, twice a week or something, that it's not worth
yes, but it's always adding a little bit more onto the particle spectrum.
Yeah, exactly. Many times it looks that they are more interested in the 9th decimal or 20th decimal rather than the first decimal.
I think they're frightened of principles. That's the problem. We don't educate them to think about principles. We tell them to get on and solve the problems.
And of course, now the theory of relativity has such a strong position in today's physics and the teaching of physics that it's very, very difficult to accept that that's probably not the way to go. That relativity is something completely different than what they expect.
Yeah, but I'm saying that quantum theory is completely different from what they're saying it is. And it's interesting, and because I sometimes talk to Roger Penrose.
Yes.
You know, I could say we grew up together at Birkbeck. We were.
I see.
Yeah, he went astronomical, of course, but I went.
Yeah, Penrose probably could be interested also in this kind of thing.
Yeah, but he wouldn't like the way you present it, because he doesn't understand the concept of wholeness.
I see.
This is the big thing. They just, although he has the idea of global energy, because that comes from Hermann Bondi.
Okay.
Bondi popularized that as I was growing up, which is where I got it from and why it's a bee in my bonnet. But he was looking at gravitational waves, and in the gravitational waves, you cannot localize the energy.
Yeah, so that also I checked how the emission of gravitational waves looks in my dynamic universe framework. It works, but I rather call them mass waves rather than gravitational waves. Because potential energy alone can't carry energy. So that we always need the mass and the balance of motion and gravitation.
Yeah, that's a very nice idea, mass energy. But then you see, you've got to explain. They have to understand what mass energy is. If they think they understand what it is, but you're using it in a different way.
Yeah.
That doesn't necessarily have an agent carrying it. Because they want to identify the agent. What's its spin? What's its quantum number? What's it this? What's it that?
Yeah. I could. Okay.
And that stops. It almost stops them from thinking in this other way. Well, what I'm going to do is, when I can find a bit of time, is to actually look a little bit more closely at what you've done.
Okay.
And I will then see whether whether I can add anything by coming in from the bottom up, trying to meet somewhere. If you understand what I mean.
That would be really nice. Yes.
But I can't guarantee anything. I mean, at the moment, I'm just working on what you have been saying, and I must look at it a little bit more deeply.
Yeah. Yeah, you can find some of my papers on the Physics Foundation Society page, so that
right. No, I look closer.
Of general description is the paper from a year ago, which was published in Physics Essays, for example, and more cosmology was. In September this year, I participated in a cosmology conference in Prague here in Europe, in Czech Republic, and I got some positive response from there, but also majority of people there who were looking the phenomena in the standard framework. They had very, very difficulties to understand that we don't need the Einstein field equations. They are very confusing. And in fact, what I have shown exactly is that the equivalence principle, which is behind the general relativity, is not correct. And in fact, you could find that in one of the slides I showed, which was that when we get motion in free fall, we get it against reduction of the rest energy.
Yes.
But in the case we get motion in an accelerator, we need to add additional delta M.
Yeah, I must look at that very carefully, because
so
Louis de Broglie had very much this idea of the rest mass being used as a dynamic variable.
Yeah, so it simply means that velocity obtained in free fall is not the same as velocity. The process is different, because in the first case, total energy is conserved. In the second case, total energy of the object is increased.
Yeah.
And in fact, we can find, I have analyzed that, what it means in celestial mechanics also. And people, as you know, the great celebration of general relativity was the perihelion, the explanation for the perihelion advance of Mercury.
Yes.
But if you make the calculation not only for one cycle, but instead for 1 million cycles, then there's a small term, cumulative terms, which added the radius also.
Yeah.
And the Mercuries had been thrown out of the solar system already. And it's exactly the same term that makes the vicinity of black holes unstable. When I correct that with my conservation of energy, we can find very nice celestial mechanics down to the critical radius. And also we can find that close to the critical radius, which is only half of the Schwarzschild critical radius, there are slow orbits which maintain the mass of the black hole. So that there is no mystery left in black holes.
Oh, there's always mysteries left. But I see it.
But let's say that the mass of a black hole is not a mystery, because we can see that they are the slow orbits which maintain the mass. And we can also accept that mass, non-structured mass, which makes it possible to pack it such densities, which there must be, which we have there. Yeah.
Good. Very good. Thank you, Paavo, for introducing me to this gentleman.
Right. Thank you. Thank you for joining in. And I think, you see, I guess I'm just thinking about, Basil was asking, what can we do? We did, of course, one question is maybe more like the physics question, like, whether the two approaches can meet and develop those ideas. And then, of course, there is this sort of philosophy of science perspective, which would be perhaps to compare. Of course, one could sort of compare and contrast the approaches, like, Tuomo Suntola.
Yeah, well, that I would give you that job, Paavo.
Yeah, that's right. But but of course it is difficult in the sense. So we've been thinking a little bit also with Tuomo. We might have at least two candidates for a PhD student. One of them more in philosophy, one of them more in physics. And somehow I feel I'm also going a bit back and forth. But listening to today's discussion, it's probably take somebody who has the physics background, because there are, like, three things. There's the standard approach, then there's Tuomo, and then there is Basil. So in a way, it's a demanding. I would imagine that it is a demanding project for anybody to really be able to deal with it. But we have, this is something we can.
Oh, but that's our role to help.
Yeah, absolutely.
Because what we've done is to find this out the hard way. We've made mistakes, and then we've been told off, and we've thought about them, and so on and so forth. And that takes a long time.
Yeah.
But when you've already done it, you can guide people to what you feel are the real difficult points of each approach.
Right. No. Okay. No.
I will do the very small. Timo can do the cosmology, and you can sit in the middle and try and put the philosophy together.
Easy. Helppoa kuin heinänteko is easy as haymaking, we say.
Yeah, well, I know you make a lot of hay in Finland.
That's right. But of course, then there is I think for example, in the case of Tuomo's approach, one could or the same, or maybe for both, is that one could look at it that if the two approaches give the same predictions with experiments, then the question is, well,
yeah, but they don't. We're giving we're giving the right experimental result. We're agreeing with the experimental results. You see, that's one of the disadvantages. We're not finding something which gives a different experimental prediction, which people can then go and look at. That's why the physicists don't like it.
It's a very big problem, because all the experiments made today, they are based to the framework of present standard cosmology and standard physics, so that the experimental setup and first of all the interpretation of the result becomes quite different. And what is very common in cosmology, that people explained observations is they say that something has been observed, although they explain the interpretation of an observation. It's completely different. For example, dark energy. Nobody has observed dark energy or acceleration of the universe. What they have observed is the increased wavelength and magnitude or brightness ratio. That's what has been observed.
But that depends upon a theory, of course.
That's it.
The theory says one thing, and what they observe is another thing. And then they're all tearing around trying to find the explanation. I'm talking with a person who's actually involved in the dark matter experiments at UCL. So I'm getting a bit of background from what they're actually doing, and he thinks, for example, that what I'm doing is probably the right way to find the solution. Now, if my way is similar to yours, I think it is in principle, then we're agreeing. You don't need dark energy. It's in the actual theory itself, because we've got it wrong.
I clearly noticed that you have had some similar thinking, because you adopted so quickly some of the ideas I presented. It's very exceptional, I can tell you that.
Okay, well, I mean, I've been thinking along these lines for a long time, as Paavo will tell you. And I think it's the right way to go. But then I can say that now, you see, because I couldn't care less whether I upset all the big boys or not. One of the troubles that I find is the youngsters don't want to stand out against the crowd. Because they are risking their career. They're not independent thinkers, simply because the system discourages independent thinkers. I mean, that's one of the things that David Bohm and I spent a lot of time discussing. How do you encourage people to think independently? I don't know. Even now, I tell some of my students some things, and they sort of look at me and say, "But that's not what everybody says." And I said, "I'm sorry, I couldn't care less what everybody says. Is it right or is it wrong?" But that requires it requires a very different attitude, actually, very different from the education we give them. You see, don't know whether Paavo told you, but I didn't have a formal education until I was about 13. So I grew up in India during the World War II. And we were traveling around, and the education I got was, okay, I learned to read and write. And I was gifted with a bit of mathematics, which I did myself. I didn't get taught it. My mother was enlightened enough to buy me books on mathematics. and I would work with them by myself rather than go to school. So I have that freedom of working outside any system. And when I became part of the system, I suddenly realized we had to play a game. And the game was, if you want to get a good mark, you tell them what they expect the answer to be, not tell them what the answer should be.
Yes.
I mean, I even went up and showed a proof that a guy had put on the blackboard was incorrect. A half-term exams came and he asked us to prove the theorem. So I gave him the wrong proof and I got 10 out of 10 for it. Which just shows you then we're not teaching. We're doing something wrong with our teaching. You realize that, Paavo, did you? That was the classic way of testing what they wanted. Give them the wrong answer and get maximum marks for it. It's quite extraordinary. Because I sat there and looked at the question and I said, well, shall I give them the correct answer? And I said, no, let me try. I'll give him the wrong answer, the answer he gave me, which is incorrect. And he agreed it was incorrect. It wasn't that he was unaware of the correct answer. But I got 10 out of 10 for maximum marks.
That's really the game, huh?
It's a game, unfortunately. They do teach you stuff, but when they test you, you know, the sort of questions that people asked me when I was teaching, are we really going to be questioned about this in the exam? Which was so depressing. No, I'm trying to teach you some physics. I'm trying to teach you to think about these things. And that's what we're up against, I'm afraid, Tuomo. That's what we're up against. But never mind. I think I'm winning now. And I think with the input that you've just put in, that'll help me with this rest mass problem that I've been scrambling with. Okay, Paavo.
Yep.
So shall we break up now and perhaps meet when later? Or you want me to join you for this discussion with this young lady, Paavo?
Yeah. How does it look like tomorrow?
Yeah, okay. While everything is still fresh in my mind.
Right. So maybe we could do that, and that could be. Is there a time? What time would be good?
Well, exactly the same time today would be very good.
Like
11 o'clock UK time.
Yeah. Okay. Very good. And
because by that stage I've woken up and I haven't got tired.
Okay.
That's good. And
I'm sorry, when you reach my age, you have to take that into consideration.
Yeah. Very good. So we could do that, and I could confirm that, and then
I mean, do you feel happy, or are you're looking a bit puzzled?
I'm always puzzled with these difficult things. I can see I'm very happy that I did somehow talking, listening to Basil, and I was expecting that there could be sort of common ground with this notion of energy, and I know that Basil, for example, doesn't think that the wave function is as important as people take it to be, and it's probably not also for Tuomo, the wave function is not the key.
It's not key. He's trying to fit his ideas into the wave function.
Yeah. One very interesting question is that how much the concept of wave, mass wave, can cover what we do with wave function.
Right, right.
Yeah. I mean, the wave. For Tuomo, the wave is important because he's got, you know, he's a practical man. He's a technician,
Right.
And he's got dipole areals which he uses, and that's a good example. But just because you got that dipole illustration doesn't mean to say that everything it must be done in waves. What I have to show is what I'm doing can be put into wave theory. That's the difference. He's coming down from cosmology, putting it into wave theory. I'm coming up from the underlying structure, which I see has not got waves in it, and reaching up to the wave idea. Because the wave idea, I think, is very limiting, even from the bottom upwards. You have nonsense there, Paavo. You have absolute nonsense with the idea of the wave in quantum theory. I'm sorry, I think the wave-particle duality is just a load of crap.
Yeah, if we look the resonator description, it already says that the structure is the thing which makes mass work like a particle.
And the wave is just...
And what is essential for quantum, the quantum is simply the amount of energy a single oscillation cycle of a unit charge can emit into a cycle of electromagnetic wave, whether it's localized or whether it's divided uniformly in all directions. It depends the type of antenna, as we know from the radio technology as well.
Yeah.
Good. Okay.
Okay, so that's where we've got the common ground. We both dismiss the wave-particle duality nonsense. It just doesn't make sense, Paavo. And I know you guys, you philosophers, try to make sense of it, but forget it. It doesn't make sense. You've got to do something else.
One of the problems today is that the physicist has such an authority that they tell the philosophers how the world looks like, and please try to make an understandable explanation for that.
Yeah. But the physicists have got it wrong, you see. That's the problem.
Exactly. So that we
they've got a partial answer, but
we have to start with philosophy that makes sense.
And that's the problem, Paavo. And you've got to teach a lot to your guys there.
Yeah. That will be...
It's no good scratching your head and just saying yes.
We got the...
You've got to do something about it.
Yes.
Good. Okay, but we will continue, and I guess with Tuomo, then Basil will look into...
It would be very nice to continue this discussion someday. A little bit more, let's say, more prepared, so that I can focus the topic we are discussing a little bit.
Yes, because I could present something now which you would not know how it relates to what you're doing. Because I haven't thought about how to relate it to what you're doing. In detail. I mean, I can see areas where we would certainly agree. And there are going to be areas where we disagree. There'll be areas where we disagree. That's progress. Without disagreement, we don't get any progress.
Good.
Okay. Well, I am getting hungry now, Paavo.
Okay, we'll let you go.
Because don't forget, you're 2 hours ahead of me, aren't you?
That's right. That's right. So we can just stay for just a little bit. We can just exchange maybe. Voidaan puhua ihan lyhyesti, jos Basil lähtee syömään.
Okay.
We'll let you go, Basil, and we'll
be... Anyway, nice meeting you, and we must continue.
Sure. Okay. My pleasure.
And Basil, I will see you tomorrow then. Yeah.
Yeah. Okay. 11 o'clock.
That's right.
Okay.
Okay. Bye-bye.
Bye-bye.